Hello, good afternoon.
Good afternoon, ma'am.
Good afternoon, beta. How are you?
I'm doing fine, ma'am. What about you?
I'm fine, thank you. Hello, Tehreem.
Assalamualaikum, ma'am.
Walaikum salam. How are you?
Ma'am, I'm fine. How are you?
I'm fine, thank you. बाकी बच्चे कहाँ हैं? Okay, let's give them a minute to join. Okay.
Okay, ma'am.
Hmm. Durdana is here. Hello, Durdana.
Hello, ma'am. How are you?
I'm fine. How are you?
I'm fine too. Thank you.
Okay, great. Hello, Durdana.
Hello, ma'am.
How are you?
I'm fine, ma'am.
कौन रह गया? Okay, so we have Shajil is not here. क्यों भाई? I think he was joining before. Let's see if he sent a message on the group. Hmm. So there's no message. Ah, Shajil
Good
is
evening,
here.
ma'am.
Hello, Shajil. Shajil.
Hi, ma'am. How are you?
I'm fine, thank you.
Ma'am, actually, I couldn't find the values of those excitation states of the items.
Actually, the values
So,
are
can you?
given in the book. You know that.
Yes, ma'am, they are.
They
Yes,
are.
ma'am.
So if you just need to find extra information, there are many sources that you can look at, but do look
Ma'am,
at authentic sources,
ma'am,
like I said before. Okay? And
ma'am, I already checked from the book. Can you tell me where I can find those values
no, in
in
the
the
book, they
sources?
are given in the article that we were studying on the same page, right?
Yes, ma'am. Yes, ma'am, I found them there. But what if I want to study further
If you
about
want to
it?
study further, you can try to follow up on the references that are given in the book, or you can go to some authentic sites that are dealing with this topic. So you can try to find them, right?
For example,
For example,
ma'am, can you guide me
matlab,
more?
you will have to
But,
search them. You will have to search them, of course.
ma'am, I actually tried to search them a lot. I even checked for articles related to this, but I couldn't find one where I could find all the values of these.
Hmm. Okay. Right. So just start by looking at the references given at the end of the book. Of course, they must contain information. But this book has been, it's a standard book, and the values given there definitely are correct and have been taken from a source. Normally, these sources are sometimes not just in the form of tables. Sometimes they're also in the form of research papers, right?
Yes, ma'am. I checked the research paper from Google Scholars. I mean, I couldn't find all the values, but I found some articles
Yeah,
which
yeah,
had
yeah.
a
So
particular,
this is,
which were designed for particular.
I cannot give you just one particular table that will give you all the values. That's the point. So
Yes, ma'am.
yeah,
That's what I was asking.
yeah,
If there is a
yeah.
particular table we can
So
find somewhere.
not necessarily, right? It's not always like
Yes,
that,
ma'am.
because when you want to go into so much detail, then you cannot find everything in one place, but you can explore as much as you want, and definitely you will find these values. And of course, the proof
Okay,
that
ma'am.
they're in the book means that they are they have been worked on, because these are topics that are continuously under progress, and from time to time people keep adding to this. So there are different ways of disseminating this information. There can be, of course, tables and charts and databases. And in addition to that, the newer work always comes in the form of research papers, right? Okay, hello,
Yes, ma'am.
Ramin.
Hello, ma'am. How are you?
Fine. Thank you. Okay, chalo, let's start. Mic band karo. Okay, so what were we talking about last time? Let's do a recap so that then we can go further.
And
Yes, kaun bol
we
raha?
were talking about
Yeah,
selection rules of allowed beta decays. It's Asad.
yeah. So we were talking about beta decays. We were talking about allowed decays, and we were talking about their selection rules. Okay, now the next person, please. Who would like to continue next?
And then we did about the examples of allowed beta decay.
This is
Illustrated
Kareem.
examples. Yes, ma'am.
Okay, so we talked about different examples of different kinds of beta decay, right? Okay, yes, next. Kareem, would you like to say something else? Kareem,
Yes, ma'am.
do you want to say something else?
No, ma'am.
जितना बताना चाहते हो बताओ, then we move to the next person. Okay?
Okay, ma'am.
Okay. So we go to the next person.
Ma'am.
Okay, yes. Who would like to speak next? We're just doing a recap of what we did last. Hanji.
Ma'am, we studied the examples and which we studied the allowed examples of allowed decays and beta positive and negative decays, and further we
Okay,
discussed
beta
the dark
decays
Fermi
can be,
decay or
just a moment.
gamma Taylor
Go
decay.
slowly, go slowly. Okay, beta positive, beta
Okay,
negative.
ma'am.
Okay, yes, Shajil. What did you say next?
Ma'am, there are two type of decays: Fermi decay and gamma Taylor decay.
Yeah, we have allowed decays are further divided into categories. One is Fermi decays, and Fermi decay. Fermi was the scientist, the famous scientist, in Italian professor who later on then worked to, went to the US and worked on the. He had received a Nobel while he was in Italy. This was, but then during the Second World War, then he had to go to the US and he continued working there. And then we have the Chemoteller or the GT decays, right? Yes, Shiji.
And then we discussed the mixed Fermi and gamma Taylor decay.
Yeah, of course, there are more complex decays also, which are not so simple, and there can be a possibility of having them a mixture of Fermi and Chemoteller decays. Yes.
And then we discussed the selection rules of the mixed Fermi and gamma Taylor decay.
Yeah, there were the different selection rules for each kind of decay. Yes. Okay, so that's it. Would anyone like to add anything?
Well, I can add.
Yes, Asad.
Yeah, so if the total change in your angular momentum is either 0 units or 1, then this decay is allowed.
Mhm.
And the total change in parity should be 0, which means that parity should remain unchanged before and after the
Good.
beta decay.
Good. So that's
And if the total change,
yes. If the
yeah, so if the total change in your angular momentum is equal to 0, then your decay is a Fermi decay. And if it is equal to 1 unit, then your decay is known as Gamow-Teller decay.
good, great. Okay, so I think we've covered most of the things, right? So this was a good overview to start to the next topic, right? So we talked about beta decays. We know there are different kinds of beta decays, and then we talked about the types of decay. What is a decay? Chalo, let's go to the basic question. What is a decay?
Spontaneous radioactive um, reaction is known as a decay.
Okay, it can be natural, it can be artificial, and we have this property of particles and nuclei that they do decay, right? ठीक है? ये तो सबको पता है
Yes,
ना?
Yes, ma'am.
Yeah, okay. And you know that we were in one of the chapters that we have studied, we talked about nuclear reactions, right? And in nuclear reactions also, we talk about decay. So a lot of the concepts around nuclear physics, decay has an important role to play around these, right? So this is also known as nuclear disintegration. It's also known as nuclear decay. It's also known as radioactive decay. It's also known as radioactive disintegration. So nuclei can be unstable. Particles can be unstable. Like, you know, there are some particles that cannot exist for a longer time, and therefore they have to decay in order to reach an equilibrium, in order to reach a state of stability, right? So we also saw that the neutron, for example, can decay and become a proton and so on. Also related to this concept, a very fundamental concepts like half-life, for example, the time that that's required for a decay to take place, right? So these are things that build on the concepts that you studied in basic physics, and then you build further on them. And again, these are also related. You start with the basic concepts. You know, there was a handout I gave you in which you had the law of decay and exponential law of decay and the terms half-life and parent nuclide and daughter nuclide and so on and so forth. Then in nuclear reactions, again, we
Yes, ma'am.
revisited these topics, right? And then, you know, in chapter number 2, we introduced you to some quantum mechanical concepts. And now in these, we are also using those quantum mechanical concepts. And example is the parity concept, right? Okay, so this is interesting, and
yes, ma'am.
it has a lot of applications. You can go towards this is a field that has applications in fundamental physics, right? Fundamental means you're working on the basic principles and laws and the basic science of what's happening, right? And this builds upon previous knowledge, and it helps develop further knowledge related to particles, related to nuclides, related to a lot of you know um, topics. You can also see, even if you look at crane and you look at the table of contents, it gives you an idea of all the different topics that come under this, right? So you can do it for fundamental research, for fundamental studies, and you can, if you're interested, and you can do it both theoretically and experimentally. Every topic can be worked on theoretically as well as experimentally. And when we combine the two, then you get a Nobel Prize. Is that right? But then again, everybody is not an expert on everything, so that's why people work in teams, and normally the theoretical part is done by experts who are experts in this, and then the experimentalists and the theoreticians together design the experiment to prove these, and when it is proven, when it's validated, then you get your Nobel Prize, right? If you are not able to prove it by both methods of theory and by experiment, you don't get your Nobel Prize, right? So there's a very nice introduction in the beginning of Crane of all the Nobel Prizes in this field. And of course, it keeps growing every year because, of course, Crane was published a few years back. And also, fundamental research can take place in uh, theoretically as well as experimentally, right? So you can also, like for example, my professor, I'm very inspired by the fact that he was working on fundamental concepts related to neutrons, and he proved experimentally uh, that a neutron is a wave. So, but he was an experimentalist. He was doing it experimentally. He's written a very interesting book about it as well, and there's a lot of interesting work that can be seen. Um, and then you have the applied side, right? So every topic has an applied side, application. So what are the applications? So there are people who are interested in applications, they work on the applications. There are people who are interested in the fundamental side of it. So from the beginning, we study, we start with the basics of the subject, and then we go further and specialize in one of the, of course, topics. Like just like you said, you could not find all the values in one place, because yes, you have to spend time and effort, plus you have to learn and gain the expertise. So therefore you choose a very niche topic for yourself, and you can go in one direction and then dig deeper, right? So what are the applied fields that these topics can relate to the topics that we are studying? Yes.
Well, its applications may include the usage of radiations in medical treatments.
Very good. So medical physics is again a vast field. Medical physics in itself has many subfields, right? You can have, just a moment. So medical physics itself is divided into many different fields. Just give me a moment. My charger has moved. Why is it moving? Yes. Okay, great. Okay. So, yeah, medical physics itself is again can be divided into many further fields. You know that there's the radiation treatment field, there is the imaging field where you use radiations for different kinds of imaging. There is the development of radiation isotopes. There is the development of these radiation or radioactivity based pharmaceuticals as well. There's a lot actually. There are different kinds of diagnostics, there are different types of therapies, there are different kinds of imaging. Every topic is very vast if you start to explore it, right? Okay, so medical physics is again a very useful application. We have a lot of work being done, as well as many practical facilities in Pakistan as well as internationally, right? So in Pakistan, there are many hospitals. Can you give me the name of some hospital?
Khan,
Aga Khan, okay. Lahore, what about Lahore?
Shaukat Khan.
Shaukat Khan, yes, they do have the PET, the SPECT, they have a radiation, of course, medical physics department, yes. Um, and we have had students who have done their projects there. Yes. What other hospital do you have in Lahore that deals with these topics? Who said they were interested in medical? I think in the beginning somebody said they were interested in medical applications.
Yes, ma'am, I am.
Tehreem, हाँ जी. नाम बताएं
ma'am.
hospital. Which hospital do we have?
Ma'am, I think so. Anmol is also doing this PET
Yes.
scans and
In Mole, yes, yes. In Mole is also a hospital that's working on these topics. Great. Okay. So again, medical physics is an application. Then power is another application, right? Then you have other fields. You have a lot of like MRI, for example, is also an application. And MRI again is related to the different properties of particles and so on. Then you can have, I don't, there's a huge, I give you information about this in the beginning of this course, right? You can go and visit the websites, and you can see like IAEA websites, right? You can see the CERN website, you can see the NIST website, you can see, again, you can go to the respective, there are many other facilities as well. So you can go to them and look at their the information. There's a lot of information that's available on these websites, and you can see the different kinds of work that can be done in these fields. And one of the reasons that I really admire for me is the fact that he was very good both in theory as well as in experiments. So he the he worked on the project for the first time where he demonstrated um, the first time the fission file. You can read about that as well. Okay, so now coming back to the decays that we are talking about, the beta decays. So I will now go here, and today we are going to talk about forbidden decays. So we talked last time about allowed decays, so this time we are talking about forbidden decays. Okay. So forbidden, what does the word forbidden mean?
Not allowed.
Not allowed, yeah.
Not allowed.
Yeah, not allowed. But basically, in this case, it's sometimes considered to be a misnomer, sometimes because here forbidden means that forbidden in this case means that these decays are usually less probable than allowed decays. So as you know that in science and in physics, we always talk about probability. There's no absolute, right? So again, forbidden does not mean that it does not occur or it never occurs. But rather, it means that it is less probable for these decays to happen as compared to the allowed decays. So if it means that there's a less probability, it means that they usually have a longer half-life. Okay. So So the most frequent occurrence of a forbidden decay frequent occurrence of a forbidden decay is when the initial and final states have opposite parodies. So this is a difference that you will notice from the allowed decays. In the allowed decays, we said that the parodies remain the same. In this case, the parodies are opposite. And therefore, the selection rules for allowed decays are violated. So thus, the selection rules for allowed decay are violated. So therefore, while it is less likely to have L is equal to 1 decays relative to L is equal to 0, decays with L is equal to 3, 5, 7, and so on are extremely unlikely. So let us start with a more probable example, okay? So let us consider only forbidden decays with L is equal to 1. So let us consider this case. So this is known as this kind of decay. These are called first forbidden decays. Okay. And like the allowed decays, they have Fermi types. So in this case, as we remember from the last time, what was a main property of Fermi decays? How did we distinguish between Fermi
That
and
the total change in angular momentum was equal to 0.
and this was based on with the spins being opposite, right?
Yes, ma'am.
So in this case, we said S is equal to 0. And similarly, the GT decays or the Gamow-Taylor decay, in this case, we had the rule that electron and neutrino spins were parallel.
Parallel.
Hanji? Okay, right. So we have now talked about forbidden decays. We have talked about the difference of forbidden decays from allowed decays. We've talked about the fact that in allowed decays, the parity was not changing. In forbidden decays, the parity changes. Okay. Again, we said that we can have different values of L, but the higher probability among those values will be for L is equal to 1, and therefore we have started with L is equal to 1. So the forbidden decay corresponding to L is equal to 1 is known as the first forbidden decay. Again, forbidden decays, just like allowed decays, can be divided into the types of Fermi decays and Gamow-Taylor decays based upon the spins, or the resultant spin of the particles. So if they are opposite, then S is equal to 0, and this corresponds to Fermi decay. And if the spins are parallel, then S is equal to 1, and this is known as a Gamow-Taylor decay. Okay, now as you know that the meeting will end in a few minutes. So when that happens, please click the same link again to rejoin the meeting. Okay. Okay, so I will also,
Okay, ma'am.
good, great. So let's also mark your attendance in this case. So I can see that everyone is there so far. ठीक है ना?
Yes, ma'am.
Yes, ma'am.
हाँ ठीक है, it's fine. I can see all of you. Eman, hello Eman. Eman, are you there?
Yes, ma'am.
Good. Durdana,
Yes, ma'am.
Ramin,
Yes, ma'am.
Shurjeel,
मैंने क्यों बोला?
Yes, ma'am.
Asad, and Tahreem.
Ma'am.
Present, ma'am.
Okay, good. Okay, so now I clear the board. Okay. So the coupling of S is equal to 0 with L is equal to 1. Okay, let's talk about this case. And L is equal to 1. So this one. Let's write it like this. So this will be, what kind of a decay will this be?
For me,
That will be a Fermi decay.
Yes, this will be a Fermi decay. Okay, and total angular momentum in this case, this will give a total angular momentum of 1 carried by the beta decay. Acha, I just remembered a student asking me for the recording of the class. Are you guys aware that the recordings of the class are regularly uploaded to the YouTube?
Yes, ma'am.
पहले से पता है ना?
No, ma'am. आज आपका मैसेज आया है.
एक उससे पहले नहीं पता था.
Ma'am.
Come
मैम
on,
सारे
मैं
लेक्चर
तो
साथ साथ ले रहे हैं
नहीं बेटा, ये
तो
तो
जरूरत नहीं पड़ी.
आपको पता है ना कि रामीन क्लास में रामीन ने भी मुझे हेल्प किया है. मेरे ख्याल आप लोगों ने, असद ने, शजील ने, डिफरेंट लोगों मुझे
Yes, ma'am.
दे रहे हैं टू रिकॉर्ड द क्लासेस. यू रिमेम्बर दैट? एंड वो रिकॉर्डिंग करने के
Yes,
बाद
ma'am.
कहाँ जाती थी? वो रिकॉर्डिंग वो यूट्यूब पे जाती थी.
Yes, ma'am.
पता है ना आप लोगों को? सो टू कीप योरसेल्फ अपडेटेड यू कैन सब्सक्राइब योरसेल्फ सो दैट यू आर नोटिफाइड. ठीक है ना? आपको पता है, आप लोगों को तो मुझसे ज्यादा पता है. यू यूज दिस स्टफ अ लॉट, है ना? आपको नोटिफिकेशन आ जाती है और फिर आपको जैसे मैं अपलोड करती हूँ यू कैन नो ओके इट्स देयर. ये आई एम जस्ट आंसरिंग दिस क्वेश्चन बिकॉज अ स्टूडेंट स्पेसिफिकली आस्क्ड मी वेयर the recording could be watched and I was surprised that I've already shared this with you. है ना? ऐसी बात है ना?
Yes, ma'am.
हाँ, तो फिर तो अगर आपको नहीं पता चल रहा तो आप सब्सक्राइब करें और उसका नोटिफिकेशन आपको आता रहे. और यू कैन, मतलब इफ यू नीड टू रिविजिट इट और व्हाटएवर, तो यू कैन ऑलवेज वॉच इट. ठीक है? सो
Okay, ma'am.
okay, so that
Okay, ma'am.
in this case we can say that delta I will be equal to 0 or 1, right? And coupling S is equal to, this was S is equal to 0 with L is equal to 1. So this was this case, and if we couple S is equal to 1 with L is equal to 1, then it will be a GT decay. Okay. So this will go with the GT decay. And in this case, the total angular momentum will be of 0, 1, or 2 units. And therefore, we can say that delta I is equal to 0, 1, or 2. So we have talked about the different cases for forbidden decays. We've talked about the Fermi case and we've talked about the GT decay. Again, in this case, we are talking about L is equal to 1, just like we started in the last, board that I have just erased. So we are coupling L is equal to 1 with S is equal to 0 in the first case to get the Fermi decay. And then we are writing the rules for that. And then we are coupling L is equal to 1 with S is equal to 1 to get the GT decays. And then we are writing the rules for the angular momentum change in that case. So this is what we've done so far. Now I'm going to erase this. Okay, so therefore we can say that the selection rules for the first forbidden decay. हमने कहा था ना कि अभी हम first forbidden decay का केस जो है वो डिस्कस कर रहे हैं. So for the first forbidden decays are delta I is equal to 0, 1, and 2. And the change in parity in this case is equal to yes. Yes means there is a change in parity, or it means that there is the parity in the two cases are opposite, right? So these are the rules based on the discussion that we've just had. And now we can go towards the examples, okay? To apply these rules and see how they work. Okay, so let's talk about the first one. In fact, we just have 1 minute for the meeting to end. So let me disconnect this meeting and then we connect to the next meeting, okay?
Okay, ma'am.
Okay, ma'am.
Okay.